My name is Robert, and I'm a tutor over at Chegg, and I tutor such topics as math, physics, electrical engineering, and computer science, mostly. And what we'll be talking to you today is about a topic that's very important in both experimental physics and in electrical engineering, which is the idea of parallel circuits. So if you've taken any course in, say, elementary circuit design or any physics lab course, probably, you know that basic circuits and circuit components can be divided into one of two groups. Components are either in series with other components in a circuit or in parallel with other components in a circuit. So what I'm going to be talking to you today about is what that means, and in particular do calculations involving circuits. So just to give you a brief review as to what's up with these guys, what I've done is on this page of the tutoring space, I show on the left an example of a series circuit and on the right an example of a parallel circuit. They both have the same components, but they're connected in different ways. So on the left, we have a series circuit where we have a battery, shown here, connected in series with three resistors, here, here, and here. On the right, we have a battery, again, here, connected in parallel with three resistors, here, here, and here. And we want to see how these circuits differ because of the geometry of the resistor placement in these two cases. So just to highlight the differences, let's make a concrete example out of this. So let's say we have a 6-volt battery connected in series with three resistors that are 1 kilo ohm, 2 kilo ohm, and down here 3 kilo ohm. So I've omitted the omega for ohm. So the first thing we want to ask is, what is the current through this set of resistors? Well, because they're in series, we know that the current going through all of them is the same. That is the definition of a series circuit. So we can replace this set of resistors with an equivalent resistance. And if you remember from your elementary circuit design class, circuits with series components have the resistances added. So the equivalent resistance of this guy, and this guy is 1 plus 2 plus 3 kilo ohms. So the equivalent resistance is 6K. And they're connected in series across a 6-volt resistor. So by using Ohm's law, we can say that the current is given by the equation 6 volts equals the current times 6K. And when you do the division, you find that I is then 1 milliamp, or 1,000th of an amp. Okay, so that's all well and good. But I told you I was going to be telling you about parallel circuits and not series circuits. So let's go over here on the right. So again, for concreteness, let's say that we have a 6-volt battery placed across three resistors in parallel. And let's say that the resistances are the same as they were before. So on the left we have a 1K, in the middle we have a 2K resistor, which that's supposed to be a K, but it's a little small. And then on the right is a 3K resistor. Let me try to fix that up real quick. Okay, that kind of worked. So that's a 2K. So the defining feature of a series circuit, as we said, is that through all the components, the current is the same. Now, what's the defining feature of a parallel circuit? For a parallel circuit, the voltages across all components in parallel should be the same. Now, why is that the case? Well, I think we would agree that the circuit on the right is a parallel circuit because it looks like the ones that were called parallel in your class. So if you look here at this node and here at this node, essentially across the battery, there's a potential difference of 6 volts that's created by the battery. The battery is supplying 6 volts of potential difference across this guy. So one would ask, well, what's the voltage across each of these resistors? So if the voltage is 6 volts above, let's call this ground. So that's ground. If the voltage is 6 volts above ground here, what is the voltage here? And what is the voltage here? And what is the voltage here? Because there aren't any electrical components here, here, or here, the voltage at all these places, here, 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 and here, is the same. Likewise, because there's essentially just a wire connecting the ground with each of these nodes, here, here, and here, the voltage there is all the same. So there are 6 volts of potential difference across each of these resistors, the 1K, the 2K, and the 3K. And that means that we can individually compute the currents going through them. So in this case, we have 6 volts across a 1K resistor, which means that the current going through this guy is 6 milliamps. So try to write that. Likewise, the voltage across this guy is 6 again. So the current going through this is 6 divided by 2 kilo ohms. So that's 3 milliamps. And then finally, the voltage going across the 3K resistor is again 6 volts. So that means that the current going through that is 2 milliamps. So when you sum that up, you get that the total current that's being drawn from the battery is 11 milliamps. So what makes this different? Well, the fact that the voltages are the same across each of these resistors is what makes this different. Over here, in the series circuit, the current is the same, which means that the voltages across each of the resistors is different, and the sum of the voltage drops from here to here to here must be 6 volts. Over here, there is no such restriction, and that's why these cases are so different. Now, finally, we're going to go through a slightly more complicated example, one that kind of puts into practice what we've been talking about. Okay, so here's a little diagram that shows a basic problem that combines both series elements and parallel elements that might be instructive. What we want to do is to give each of these components, which right now doesn't have a value because I haven't assigned them a value, values in voltages and in resistances, and to solve for the current going through these guys. So, just for sake of concreteness, let's go ahead and assign these values. So, let's say that we have a 2 ohm resistor here. Note that I said ohm, not kilo ohm. A 2 ohm resistor there. A 4 ohm resistor here. And a 2 ohm resistor here. And then we'll finish off by saying that this is connected across another 6 volt battery. And what we want to do is we want to find the current going through each of these branches of this circuit, so each component of this circuit. So when students see problems like this for the first time, they often get a little worried because this doesn't really neatly fit into the kind of paradigm of a strictly series or a strictly parallel circuit. And there's a very good reason for that. It's not. Instead, you have components that are in series and some that are in parallel, and we need to figure out how to apply each of those concepts in a way that makes sense. So let's look at the kind of big picture here. We have a battery, and that battery is directly connected to a 2 ohm resistor. And then the 2 ohm resistor is connected to this box thing that has 3 resistors in it that are arranged in a kind of weird way. And then that's it. Like that's kind of it. So what that means is that whenever we hook up this circuit, there's going to be a current flowing through all of these components. And whatever current flows through the 2 ohm resistor must flow through either this resistor or this pair of resistors in order to make its way back to the battery. And that means that the 2 ohm resistor is in series with this network of resistors here. So that's the series part of this question. So now once we figure out what's going on with this set of resistors, we can figure out how to solve the problem. So over here we see that there's a 4 ohm resistor, and then there are two 2 ohm resistors. So note that at this node there must be some voltage, and also at this node there must be some voltage, which means that the voltage drops across the 4 ohm resistor and the pair of 2 ohm resistors must be the same. So that means that the 4 ohm resistor is in parallel with the set of two 2 ohm resistors. Okay, now what about these two 2 ohm resistors? Well, as we said before, whatever current goes through the 2 ohm resistor here has to also flow through the 2 ohm resistor here in order to get back to the battery. So that means that these are in series. So the first thing we can do to simplify this problem is to say the combination of 2 ohm resistors is equivalent to a 4 ohm resistor, just like we did when we covered that other problem before. So we're going to rewrite this as, this is going to be a 4, this is a 2, there's the battery, which is 6 volts, try to draw a 6 correctly, and then hook that back up, and then again there's going to be this equivalent resistance, which is going to be 4 ohms. So now we have a 2 ohm resistor that's connected with a pair of two 4 ohm resistors in parallel. Now if you remember how to combine parallel resistances, you'll know that we can combine these two in a way that makes sense. So we know that 1 over the equivalent resistance of this pair of resistors is equal to the sum of the reciprocals, so 1 over R1 plus 1 over R2. So 1 over R would then be 1/4 plus 1/4, which is a half. So that means that this network can be replaced by a single 2 ohm resistor. So we have the battery again. I'm really good at drawing resistors, you guys. And then another resistor. And then we have, again, the 6 volt placed across the set of two 2 ohm resistors. And at this point, it becomes just like our first problem where we have a battery and then a couple of resistors in series, and then we can immediately say that the current going through each of these is the same, so the current going through this guy and this guy must be given by 6 is equal to I times 4, so I is equal to 1.5. So the current flowing through this 2 ohm resistor must be 1.5 amps. Okay, so fine. So now how do we figure out what portion of that 1.5 amps goes through the 4 ohm and the two 2 ohm resistors? Well, we know that the voltage drops across the two 4 ohm resistors here. So this guy and then the equivalent guy must be the same. So that means that essentially half of the current goes through each branch of this because they're the same resistance value. So that means that each branch gets 0.75 amps worth of current going through. So as of now, we've completely characterized the circuit. We know that 1.5 amps flows through the 2 ohm resistor, 0.75 of which flows through the 4, and 0.75 of which flows through the pair of 2 ohm resistors. So I hope that's been helpful, and I want to kind of stress the fact that the idea of parallel circuits is actually really important, and you've probably used it a lot without knowing it. In everyone's apartment and house, pretty much everyone who has electricity in their place has it through either a 120 or a 220 volt main line that comes in. That's plugged into a wall is in parallel with that voltage source. Literally everything. And so you've been using parallel circuits this entire time, your entire life, without knowing it, which is pretty cool. So I hope this video has been helpful, and I hope that if you found it helpful and you have further questions about anything involving electronics, electrical engineering, or physics, or anything like that, that you'll come find my page and hopefully contact me. All right. Thanks a lot, you guys. Bye.